sir.
So, yeah, thank you. Yesterday we were talking about the these relations. We have seen that stress is related to the strain components by means of these coefficients, and this matrix we call this as a stiffness matrix. And if you invert this stiffness matrix, then that is called as the compliance matrix. So this is the compliance matrix. So when we write strain, so strain will be equal to the this strain matrix will be equal to the compliance matrix into this sigma matrix. Okay. Okay, this is the matrix complete, means all the coefficients. So this is the compliance matrix. This is compliance matrix, and this is given as this complete matrix. Okay. So in earlier equation, this is called as a stiffness matrix. So when we write the equation in terms of stress and strain, but what are these coefficients? Means these coefficient, what are exactly these? Okay, so these values, as I mentioned, that you need to find out by doing the actual physical testings, experimental testing, and these experimental testings, as per ASTM standards, we have discussed in unit number 3, by doing tensile, compression, shear test. So we can get these constants, values of these constants. So all these C and S, basically, these are the functions of what? So that's what I mentioned here. So these are the functions of Young's modulus. These are the functions of Young's modulus, then or shear modulus and Poisson's ratio. Okay. So when a material is characterized experimentally, so the so-called engineering constants such as Young's modulus, shear modulus, and Poisson's ratio are usually measured through physical testing or experimental testing instead of Cij or Sij. Means we don't directly measure the Cij or Sij, but basically we measure this Young's modulus, Poisson's ratio, or shear modulus, and these Cij or Sij. These are the functions of, so these are the functions of all these Young's modulus E, Poisson's ratio mu, or if it is a shear modulus G in case of the shear stress. Okay, so this, then the engineering constants are also widely used in the analysis and design because they are easily defined and interpreted in terms of the simple state of strain. So here several simple tests and their resulting states of stress and strain will be used to develop 3D and 2D stress strain relationships for orthotropic and isotropic material. So 2D and 3D I particularly mention because many structures can be analyzed as a 2D structures. So if it is a flat composite plate, okay, where the two dimensions are sufficiently larger than the third dimension, which is thickness, so that can, we will not analyze this as a 3D, but we'll analyze this as a 2D. So if I take this lamina, and if I, this is small thickness, suppose this is 5 mm thickness. Okay, so this lamina, so we will generally analyze as a 2D structures. We will analyze this as a 2D structure. So here the equations that we have seen just now, so these equations can be, so these equations can be reduced further for the 2 dimensions, means these things will not be there. So this sigma 3 will not be there, epsilon 3 will not be there, and at the same time the shear stress component involving the this third number, okay, so these things will be also not there. So these equations can be easily reduced to the for the 2-dimensional structure. How it can be done, that also we'll see. So that's what it is mentioned that, so it can be used to develop the 3D or 2D stress strain relationships for the orthotropic and isotropic material. So that relations can be used for 3D or 2D structure. Now, the main question is how to find out these constants, this C11, C12, C13, like that. This constant, how to find out? So these constants are found out by doing these tests. Okay, you can see this in figures by doing this 1, 2, 3, 4, 5, and 6 independent test. So those many tests, if you are able to do, if you can do, then we can find out the relationship between the stress and strain. Means these constants we can find out. Okay. Now first we'll do one by one. Means first, in the first test, what we'll do, we'll apply the force in one direction. Okay, we'll apply the force in one direction, and at means we'll apply only the stress sigma 1. So we'll induce the stress sigma 1 only. At that time, no force is applied in the two direction and in the third direction. At the same time, no shear force is also applied. Means only the normal force perpendicular to this plane, sigma, that is 1, that is sigma 1, will be induced in this particular. Okay, and then we'll relate the stress, we'll find out the stress strain relation. In the second test, we'll keep the sigma 1 and sigma 3 as 0. At the same time, all the shear stress components 0, and we'll apply only the sigma 2. Means we'll apply the force only in two directions. So if we apply the force only in two directions, keeping all the other forces at 0, means we are inducing the stress sigma 2. Then we'll find out the this constant. Similarly, it can be done for the third, where sigma 2 and sigma 1 will be 0, and all shear stress component will be 0. In this case, all normal stresses will be 0, and this stress in 3 1 and 1 2 will be 0. Only the shear stress will be applied, or shear force will be applied in the plane 2 to 3. Other components will be 0. Here shear force will be applied in the plane 3 to 1, and here shear force will be applied in the plane 1 and 2. So this, we are simplifying this. In actual scenario, it is not always necessary that component is subjected to only one kind of load. It can be subjected to the other loads, but this is the best, easier, simplified way to find out the constant. Okay. Other tests are there, biaxial and triaxial, but that does not make much difference. So this is the way generally followed to obtain this constant. Okay. Now then we apply the theories of failure and these things to get the idea of the complex loading conditions. But in ideal case, we want to find out the what is the Young's modulus in one direction, what is the Young's modulus in two direction, what is the Young's modulus in third direction. Then we have to carry out this independent test. Now I have taken the first case in that. So one or two cases I will explain how to find out this constant, and from this then we will be able to relate this, to extend this to next cases. Consider a simple uniaxial test consisting of applied longitudinal normal stress sigma 1. Okay, so this is the lamina and the load is applied along this, that is only sigma 1, along the reinforcement direction. So this direction is reinforcement, fiber direction, suppose, okay, of a specimen from an orthotropic material as shown in figure. It is assumed that, so this sentence is very important. So it is assumed that all other stresses are equal to 0. Okay, it is assumed that all other stresses are equal to 0. Means what? So here, so this means, okay, so this sentence means sigma 1 is not equal to 0, but sigma 2 is equal to sigma 3 is equal to tau 1 2 is equal to tau 2 3 is equal to tau 3 1, all are equal to 0. Only thing, sigma 1 is not equal to 0. Then once you apply this, see, you can say here, we can plot the stress versus strain curve, and here you can get this for the epsilon also. Strain also you can get, this is for strain 2, because when you apply the force, there is a change in dimensions along the longitudinal and transverse direction. This will give us a Poisson's ratio. Okay, so ratio of the transverse strain to the longitudinal strain, that will be the Poisson's ratio. Okay, now after doing this, what equations we will get? See, this, and how this you can see here. Now I will just Now this equation you know, right? From this equation, just try to understand now. So from this equation, so if you have this sigma 2, sigma 3, sigma, all these things, okay, all these things are zero, okay, all these things are zero because we are not applying this. All these things are zero. So what we will get? Epsilon 1 is equal to S11 into sigma 1. Okay, that epsilon 1 is equal to S11 into sigma 1. Or we can say that because we know the relation, what is that? Sigma is equal to E epsilon because this Young's modulus in one direction. So this will be the epsilon 1 will be equal to what? Sigma 1 upon E1. So this S11 is nothing but, what is this S11 then? Epsilon 1 is equal to sigma 1 upon E1. So S11, this indicates that S11 is equal to the 1 upon E1. So we got this constant S11. Okay, so this is clear now. Now we have the this epsilon 2 relationship between the epsilon 2 is equal to, because this is a Poisson's ratio, nu 1 2, Poisson's ratio nu 1 2 is equal to epsilon 2 upon epsilon 1. That is the strain in transverse direction divided by the strain in longitudinal direction. So this will give the Poisson's ratio. This can be further simplified as just by putting the values of this epsilon 1 that we have found out. Then we can get the epsilon 3 as a 1 3 epsilon 1 because elongation, as in earlier case also we have seen that this so this shear because there is no shear stress induced in this, and this is a, so shear strain components, all shear strain components will be a 0. Now in this case, just remember these relations, this one and this one, this will be obviously 0. So here again see that in the for other cases, what is the epsilon 1, epsilon 2, and epsilon 3, how it will be related to these coefficients S11, S12, and S13. So let us see how the compliance matrix and engineering constant of an orthotropic material are treated. So we are on the same case that apply sigma 1 equal to 0 and other stress components are 0. So what we'll get here, so first equation I have shown you. What is that first equation? Because all these are 0, okay, because all these are 0, sigma, all these are 0. So first equation epsilon 1, so this epsilon 1 is equal to S11 sigma 1, because next things will be a 0. If I write epsilon 2, so we are in the this equation. So S21, okay, S21 into sigma 1, and next S22 will be sigma 2 0, S3 this 0, all these 0 means next things will go on 0 for this case. Okay, so this will be a S21 or it can be a S12 because we know that this is a symmetric, so that will be equal to the sigma 1. So we got this equation, we got this equation. Third equation will be how? This epsilon 3 will be what? So these things again will be 0 because these are going to multiply to this constant, to this stress components. Okay, so this will be a S31 multiplied by sigma 1. Okay, S31, so like this, S31 multiplied by sigma 1. So epsilon 3 will be equal to S31, or it can be rewrite S13 because this is a symmetric, will equal to sigma 1. So here you got all the components. S11 is what? Epsilon 1 upon sigma 1. S12 or 21 is what? Epsilon 2 upon sigma 1. And S13 or 31 is equal to epsilon 3 upon sigma 1. So we can get the this all these S1, these components we can get in terms of the stress and strain. So now again further simplifying this, just we can simplify this. Already we have seen this sigma epsilon is equal to sigma 1, or this can be written as this, okay, from the same equation. Now I want to find out the Poisson's ratio. So this is S11 is equal to S11 is equal to this one. Okay, this we have seen. Now Poisson's ratio is what? mu12 is what? That is epsilon 2 upon this epsilon 1. Or this ratio, so if you take this epsilon 2, okay, epsilon 2 divided by epsilon 1, what will get? S12, sigma 1 will get cancelled, and this will be a S11. So you got the mu12. Okay, so this is clear. Now again further I can find out epsilon 13. Okay, epsilon 13 will be a epsilon 3 upon epsilon 1. And if you take the ratio of this epsilon 3 and epsilon 1 here, okay, if you take the ratio of this epsilon 3, that is S13 divided by S11, so this will give a S13 upon S11, sigma 1, this and this will get cancelled. Okay, so minus of this, you will get this. So if you look to these equations, these two equations, this one and this one, what will happen? You can just, in general, if I try to write this, so this mu12 is 2 upon 1. 13 is 3 upon 1, means these digits goes to the numerator and these digits goes to the denominator, right? These digits go to the numerator and these digits go to the denominator. So Vij in general, if I write a Vij, so this will be a defined as the ratio of negative of the normal strain in direction J to the normal strain in direction I. So V, this new Ij, I can define as epsilon J divided by epsilon I minus of this. Okay, in general we can write. Similarly, I can write this as a mu13. Okay, that will be a, this digits O will go the numerator epsilon 3 upon epsilon 1. So again, if you take this ratio here, you will get this equation. So Poisson's ratio, just one remember here that Poisson's ratio, you cannot write this as a 1,3 is not equal to 3,1. Okay, just remember, this is not a, it is applicable for these coefficients, but not Poisson's ratio. Don't make jumble here. Okay, this is not symmetric. So 1,3 will be a like this. 3,1 means it will be a epsilon 1 upon epsilon 3. Okay, so don't, this is called as a major and minor Poisson's ratio. That we'll see quickly. I think this is clear. If anybody has doubt in this, you can quickly ask, or we'll go for the further. Now taking the second case, and second case is that when we apply this force in the two directions. Okay, when we apply the force in two direction, so in this case, what is there in this case? So sigma 2 is not equal to 0. Okay, but sigma 1, sigma 3 and all other shear components will be equal to 0. Okay, all other, that I will not write here, but all other shear component will be 0. Sigma 2 is applied to the same material with the other stresses being equal to 0. Now the experimental observation is that resulting strains can be expressed as, okay, so we can write this again by referring to this equation, right? Epsilon, because this is 0, this is 0, all other 0 now. Okay, so all other, I don't know whether you are able to see at the okay, so this, so you will get here epsilon 1. Okay, I will get epsilon 1 will be a S12 into sigma 2. Okay, epsilon 2 will be what? S22 into sigma 2. So epsilon 2 will be a this way. Epsilon 2, I can write epsilon 2 is equal to what? S22 into sigma 2. Or again, we know that the sigma 2 is nothing but E2, E epsilon into epsilon 2. So this sigma 2 upon, so here sigma 2 upon epsilon 2 will be a E2, or E2 can be written as a reciprocal of S22. Okay, that way. Similarly, we can write this epsilon, epsilon 3, and all other components are 0. So this we can write similarly as we discussed in the previous case. Okay, so here sigma 2 is not equal to 0, sigma 3 is 0, all other stress components. So we got this equation. Similarly, we can write this. Okay, and that is the new. Okay, I mean quickly I will write here new 1 2 is equal to what? Epsilon 1 upon epsilon 2, and epsilon 1 upon epsilon 2 ratio. If you take, then you will get this one, because now from again just quickly again I will write what is the epsilon 1. Epsilon 1 is equal to, because this is 0, this is 0, this is 0, this is 0, this is 0. So epsilon 1 is equal to what? It will be a S12 into sigma 2. Epsilon 2 is equal to what? S22 into sigma 2. And epsilon 3 is equal to what? So epsilon 3, this is 0 and this is 0. Only second will be a, this will be a S32 into sigma 2. So nu 21 epsilon 1 is what? Epsilon 1 is S12 sigma 2, and epsilon 2 is what? S22 sigma 2. So minus of this. Okay, so this will get cancelled. So that's why, so S12 upon S22. Okay, so this is what we derived here. Similarly, you can derive this and like this. All these things, and this is the for this case. Don't get confused. This is for which case? This case. In earlier case, this was 0. Again, if you go for the sigma 3 is not equal to 0 and all other 0, then these relations accordingly will change. And then accordingly these relations will change, and accordingly these relations will change. So you have to find out this accordingly, the Poisson's ratio. So this is called as, okay, in the earlier case, this mu12, okay, mu12 is called as a major Poisson's ratio. It is called as a major Poisson's ratio, and 21 is called as a minor Poisson's ratio. Okay, this is just representation. Just remember this: 1 2 is a major Poisson's ratio and 2 1 is a minor Poisson's ratio. And how to calculate that, just now I discussed with you. So accordingly you can find out this major and minor Poisson's ratio. Now similarly, this sigma 3, now third case. So this is the third case. All cases I will not discuss now. For shear case, I will discuss only one case. You can similarly, you can find out. So sigma 1 is 0, sigma 2 is 0, and sigma 3 is not equal to 0. And other shear stress component are 0. So you will get the E3 is equal to 1 upon S33, and this Poisson's ratio you will get accordingly. Okay, so this already I discussed, and you can apply this rule. Okay, Vij. So this way, now coming to the fourth case, that is the when we apply the that shear or other components will be 0, means here sigma 1, sigma 2, sigma 3 is equal to 0. Tau 1 2, okay, tau 1 2 is not equal to 0, and other components tau 3 1 and tau 2 3, these are equal to 0. Okay, so this is not equal to 0. So if you consider in the plane 1 2, if you apply these stress components, and if you we know that for shear stress, just like in the normal strain, what is strain is related to what? Sigma upon E. Strain is related upon sigma upon E. Similarly, here shear strain is related to what? Just consider the analogous. Okay, shear strain 1 2 is related to the shear stress divided by the shear modulus. Just like this is a Young's modulus, this is Young's modulus. So this is G12 is the shear modulus. G12 is the shear modulus associated with the plane 1 2. Okay, so similar relations you can obtain for the plane other planes 2 3 and 1 3. So in that planes you can obtain the similar relations. So after doing all these values, after taking all these values, then we'll get the final these constants. Okay. So finally we got these relations where we can see, finally consider a general 3D state of stress consisting of all possible normal and shear stresses associated with the 1 to 3 axes as shown in figure. Okay, since we are dealing with the linear behavior, it is appropriate to use superposition. Means we can directly add now here. Okay, we can directly superposition method. So that we call as a superposition theory. Based on the superposition, we can add all these resulting strengths due to the simple uniaxial and shear test as in given in equations. Okay, in given equations that is discussed earlier. Okay, that is discussed earlier, and similar equations are described above. The resulting set of equations, all the putting of the values of here. So this is what. So I have given this matrix, those S11. Okay, so this S11 represent this value. This is S12. This is S13. Then this is what? This is S21. Okay, likewise. And this is nothing but S44. This is nothing but S55, and this is nothing but the S66. So shear modulus. So here now we got all the constants for SS, this compliance matrix. So this constant, you have to remember this, or you have to find out this. Means whenever some numerical based on this is asked, means this constant you should know. We'll take one quickly numerical based on this also. Before that, okay, so this matrix you have to remember completely. And what will be the stiffness matrix? Just if you take the inverse of this, okay, now you will say the what about the C coefficients? But if you take, you know that the C matrix, okay, C matrix is nothing but the inverse of S matrix. So if you take the inverse of the S matrix, then all this, we have to take the inverse of this matrix. You can get the coefficients for this C. Okay. So now this one concept just want to discuss. You can see here the there are two coordinate systems here. 1, 2, 3 are along the fiber orientations, whereas X, Y, Z, these are at any angle theta. Okay, at any angle theta. So this is at any angle theta. So we discuss about the this equation, the previous equation I will show. This equation is for what? You might have forgotten now again. This is for the orthotropic, specially orthotropic lamina, because that's why these are got reduced zero. Okay, these got reduced zero because of the orthotropic nature. So this is for specially orthotropic material, specially orthotropic material. We got these components at zero. Okay, these components are zero. But what happens? Specifically orthotropic material means, again I will explain. So fibers are oriented either parallel to this in one directions, or these are parallel to in two directions, or these are parallel to the third directions. Okay, so either parallel to the one direction, two directions, or parallel to the three directions. These are the, means there is no fibers at an angle. There is no fiber at an angle. But here, if you consider a simple uniaxial tensile test consisting of applied normal stress sigma x along the arbitrary axis, but if you apply the force, okay, if you consider fiber orientation in these directions, or the load applied in these directions, okay, along the arbitrary axis which is inclined at an angle theta, okay, as shown, we find that the full complement of the normal stress and shear stress are developed. Means earlier we have seen that there is an independent, means other stress components are zero. But if you apply the forcing along this direction at an angle theta, the generation of the shear stress due to the normal stresses and normal stress due to shear stresses is often referred to as a shear coupling. Means when we apply the load in this direction, then there is a coupling. There is a coupling between the normal components and the normal components, that is normal stress and the shear stresses. And this is called as a shear coupling effect. As a result of shear coupling, all the zeros disappear in the compliance matrix and it becomes fully populated general 3D state of stress associated with the arbitrary XYZ axis. This is generally orthotropic material. Means what happens, if there is a load stress developed at an angle, then all the zeros will disappear. Means these values will become non-zeros values because there will be a coupling between the this means if you apply the epsilon 1, then other components will be also there. Right now we assume that other components will not be there. So shear coupling effect will be there, and that is called as the generally orthotropic material. And we discussed the earlier case as a specially orthotropic material. For specially orthotropic material, this will be a zero, this will be a zero. For generally orthotropic material, these components will not be a zero. That is the meaning of this. So just remember this, but this can be further simplified later. We'll see. The stiffness or compliance matrices for the generally orthotropic material are of the same form as those of generally anisotropic. Means it is as good as an anisotropic material. Okay. So obviously then the experimental characterization of such a material is greatly simplified by testing specifically orthotropic material. Then I will show you that by testing the specially orthotropic material, for such material also analysis can be done by taking the off-axis coordinate system into picture, means by transformation of the coordinate. Okay, this we'll see later on, but similar test results, the purpose here is that similar test results which are obtained for the specially orthotropic material can be extended for the generally isotropic material by taking the off-axis coordinate system into account, or by knowing the relationship between the stresses along the normal direction, stresses along the applied in the at an angle theta. So that transformation relations once we get, we can extend the constants of light. We can use the constant of obtained under this condition to this condition. Okay. So now these things, if you are not understood, we will be discussing further in detail. Just wanted to give background. Now again further we are going to simplify these equations. Okay, whatever problems we are going to solve, it will be for the 2D case, not for the 3D case. So here, and that's why I am discussing the topic that is the reduction of Hooke's law in 3 dimension to the 2 dimension. Okay, reduction of the Hooke's law from 3 dimension to the 2 dimension. Why it is possible? This is because mostly we are dealing with the composite laminate having the smaller thickness. And if composite laminate, just imagine a thin pad. Okay, just imagine the thin plate. So for the thin plate, what is happening? The x and y dimension, length and width are considerably larger compared to the thickness. And if the thickness is very small, this structure can be assumed as analyzed as a 2D structure. Okay, and that's why we have to reduce this equation from 3 dimension to the 2 dimension, and this 2 dimension equation we can apply to the again orthotropic. Okay, orthotropic. Just bidirectional lamella is orthotropic, unidirectional lamella is orthotropic. Okay, so in that case, what happens? We have this equation for the 3-dimensional case. We have this equation for the 3-dimensional case. But for the once you reduce it from the 3D, once we reduce it from 3D to 2D, what will happen? All these components having the third digit, this one, they will be a 0. They will not be there. Okay, they will not be there. So what will happen? So this third row and this third column, I can completely cancel it. Okay. Similarly, this 2, 3 and 3, 1 will not be there. So this I can cancel. This I can cancel. Then this is what? This is 4th row and 4th column. So this 4th row, 4th column, this I will cancel. Then what is left? So what is left is shown in here. Epsilon 1 is there, epsilon 2 is there, and gamma 1, 2 is there. So epsilon 1 is there, epsilon 2 is there, gamma 1, 2 is there. And these components, S11, S12, S21, S22, S11, S12, S21, S22. So this is 0. this is 0, this is 0, and these two fellows, these are 0. Okay, and this is remaining only S66. Okay, and this is tau 12. This is tau 12. Okay, and this sigma 1 and sigma 2. So this is the simplest equation. Now we are much comfortable in handling this equation. This is the equation for the 2D orthotropic lamina. How many constants are there? How many you need to find out? Only this 1, 2, 3, and 4, because this is a symmetric. Only just 4. Okay, just 4 constants you need to find out here. So, and already these values we have found out. Already we have found out these values in earlier equations. So we have S11 is equal to this, S2 is equal to this, S12, S21 is equal to this, and S6 is equal to this. So this you have to remember, these values you have to remember to solve the numericals. This value you have to remember to solve the numericals. And how many? 5 non-zero compliances. 5 are there. 1, 2, 3, 4, 5. 5 are the non-zero. 5 are non-zero. But since one is symmetric, so only 4 independent compliance constants are there for the spatially orthotropic lamina. This is the case for spatially orthotropic lamina, and this is which case? This is 2D case. Okay, this is a 2D case. So this equation, now we have arrived these equations, and what are the corresponding values, that also we have discussed. Now you will see if you write this in a stress strain relation. Okay, so again these values I have written here for your ready reference. If you write this, so this matrix is again written. Okay, similar matrix, or by putting the values of the coefficients here. Now invert, so if you want to write down the stress strain relation, so invert this S matrix. Compliance, take the inverse of this matrix. Okay, just take the inverse of this matrix. You will get the sigma matrix into this what is here we are calling this as a Q. Again notations. Okay. So sigma is equal to this Q into epsilon. Okay, or C you can say. Epsilon 1, epsilon 2, gamma 1, 2, sigma 1, sigma 2, and this is. And what are these? If you take the inverse, याचा inverse जर घेतला, okay, if you take the inverse of this, you will get these constants. You will get this. In terms of S, this will be a this, or if you in terms of, म्हणजे याचा inverse घेतला तर तुम्हाला हे मिळेल, ह्या व्हॅल्यूज मिळतील, आणि याचा inverse घेतला, याचा inverse घेतला, तुम्हाला हे in terms of this मिळेल. Okay, again these both values you have to remember, and this will help you to. Now take an example, one quick example, we will solve it. I have taken the solved example from the author book only, but just for the complete set of completions, means you should also go get to know that what kind of examples we will be studying. Okay, so here I will discuss this example, but numericals you have to go through the books, you solve on your own. I will not discussing numericals because most of the solved numericals are there in the books. For graphite epoxy unidirectional lamina, find the following. Okay, find the compliance matrix. So compliance matrix means what? Where all S coefficients you have to find out. All Sij coefficients you have to find out. Compliance matrix. You have to find out the minor Poisson's ratio. I have discussed the major and minor Poisson's ratio. You have to find out the reduced stiffness matrix. Stiffness matrix, that is the Q matrix. You have to find out the Q matrix or C matrix, where the means sigma, where sigma relates to the strain matrix. Okay, this matrix means inverse of this. Okay, Q matrix is nothing but the inverse of S matrix, and the strain in 1-2 coordinate system, that you have to find out the gamma 1-2. And the properties are given. Sigma 1 is given, sigma 2 is given, tau 1-2 is given. Okay, shear stress components are given, and you have to use these properties for this lamina. Means Young's modulus and Poisson's ratio, shear modulus, all these properties are given. You have to find out the respective these matrices. Now coming one by one, compliance matrix we'll first find out. We know this compliance matrix, and we know all these coefficients S11, S22, all the values are given. So you have to, so all these values E1, E2, these are given. So you can find out the accordingly. So you will get the S11 is equal to this one. E1 is there because it is a reciprocal of E1. So you will get this unit. Just see unit. Unit is important because unit of the, this is a GPA. Okay, or here they are mentioning Pascal. It is okay. You stick to the GPA or MPA like that. Okay. But inverse of this, then S12. So S12 is what? This, and Poisson's ratio divided by E2, and E2, sorry, S12, this 12 upon E1. So 12 is given, 21 is not given. Okay, these are not same, but ratio is same. Okay, so 12 is given 0.28. 12 is given upon E1 is given this one, so we can get this. Similarly, you can find out this S22 and S66, which is a reciprocal of this shear modulus. Okay, this one. So once you get this, means you got all this S matrix. Okay, and then next, what you have to find out, the this Q matrix you have to find out. Either you find by using these equations, or if you are able to take the inverse of this. याचं इनवर्स फाइंड आउट करणं जर सोपं वाटलं तुम्हाला तर इनवर्स फाइंड आउट करा. आय डोंट नो वेदर इन कॅल्क्युलेटर यू आर एबल टू फाइंड आउट द इनवर्स ऑफ द 2/3 matrix. I think it is possible. On calculator you are able to find out the inverse of the 3/3 matrix maximum. Okay, so if you are able to find out, then all these calculations you need not to do. Directly you will get the this inverse of this matrix. You will get these coefficients at respective places. Okay, or if you are not able to find out the inverse, you can find out the respective values by putting these values. In that case, you have to remember these values, all these. Okay, so if you are not able to find out the inverse, then these equations you have to remember. Yes, so these are the answers. We can I have taken the solid exam from author book, so I will not discuss further here. Strains. Now you have to find out. The next is a shear strain you have to find out. Now this thing is given, right? Means these, all these coefficients are sigma 1, sigma 2 is given. So sigma 1, sigma 2 are given. So you just put the values. Okay, just put these values. All these stress components are given. Only thing, what job you have to do? You have to multiply this 3/3 matrix with 3/1 matrix, and this will result into the 3/1 matrix. So multiplication of this matrix will give you this constant. So these things you have to practice it, because for questions you need to find out the final answer. That is most important.